See in this third class of this interference, we have to study one experiment, that is determination of wavelength lambda of monochromatic source using bioprism. Usually they will ask this as a 10-mark question. So first you should know what is an experimental arrangements and how it is adjusted, how the values are determined. You know that in the last class your fringe width beta is d lambda upon d, or this is lambda is equal to beta into d, that divided by capital D. That means by the experiment, to determine this wavelength of monochromatic source, you should know what is B. B is nothing but fringe width, and small d is distance between coherent sources, and capital D is distance between coherent sources and the screen. Then to find out this experiment consists of a long metal bench. That metal bench is called as optical bench. This bench is known as what? Optical bench. And it is graduated in centimeter. That length of that bench about 3.5 meter. Then there are 3 vertical stands mounted on this optical bench. So on one stand an adjustable slit is fixed. This slit can be adjustable. It may open or it may close, just you have done in the spectrometer experiment. Then it can rotate also like this. If you rotate this screw, entire thing rotates in this direction. And if you rotate the entire ring, this slit closes and opens. It is called an adjustable slit. Then on the second one, a biprism is placed. All of them are vertically mounted, perpendicular to the length of this bench. And in the third stand, there is an eyepiece. You can observe the fringes through this eyepiece. Then see here, there is an eyepiece and prism, and one more thing is here, adjustable slit. See, this is about experimental arrangements. See here, these 3, this can slide along this bench, it go in this direction, or also it moves along this direction. And same thing for this also, it moves in this direction or it moves in this direction. So same thing for this also. They slide along the length of that optical bench. Then there is, on the horizontal scale, horizontal metal strip, this is also graduated in centimeter, like that in traveling microscope. If you go on rotating here the screw, this traveling microscope shift in this direction and comes out. So similarly all these three. So they can move in this direction also and they move in this direction also on the optical bench. Then source of light whose wavelength has to be determined is placed here. And first all these three are adjusted at same height. In other words, they are coaxial, same height. Then you go on adjusting this slit. Then at a particular distance between this prism and the slit, you can observe two images of the slit of equal brightness. Two images of the slit. See, if you, I told that it is possible to move all these three. So keep this eyepiece constant. Keep slit width also at the same place. Make it as narrow as possible. Then this slit should be parallel to the edge of this biprism. Then if you go on moving this biprism at a particular position of the biprism, you are going to get two images of the slit of equal brightness. Then keep this as it is, which is shown here, the slit, biprism and eyepiece. Then fix this position. Then go on moving this eyepiece. The next is go on moving this eyepiece slowly towards this biprism. At a particular position of the eyepiece, so you are going to observe the fringes. You are going to observe a fringes. And focus the crosswire of this eyepiece on a particular bright fringe at the center. Bright fringe at the center. Then you know this is also graduated. And note down this position as x0. On this horizontal scale, by focusing on the bright fringe, note down the position x0. Now you know that you are x0. And by rotating this screw, shift this crosswire to the second bright band. Then third bright band, fourth bright band. Like this, you go on moving up to nth bright band. I think this will shift somewhere here, and note down this as xn. Now your fringe width beta is xn minus x0 divided by n. Or you take this as capital N number of fringes, this xn divided by x1 minus x0, 0. What we did is, first focused on one bright fringe, x0 is noted, then go on moving about 10th fringe, so that distance is noted, so xn minus x0 upon 10 will give this fringe width. Then this distance d, the distance between this slit and eyepiece, there is a scale on this. The distance between the slit and the eyepiece directly will give what is d. Then you have determined beta and d. Next, to find out that small d, the in between this biprism and eyepiece here, a convex lens of short focal length is introduced. Then, by seeing through this eyepiece, the lens is moved. When you move lens towards the biprism, then fringes will merge. You are going to get two enlarged images. So that means when is object distance is u and image distance is v. This lens is moved. You are going to get enlarged image. Measure the distance between them is d1 with the help of this scale. Then go on moving this lens to another position, L2. L1 and L2 are not two separate lenses. They are the position of the lenses. Only one lens is used. Once it is placed at L1 and it is moved towards the eyepiece, and at some position a diminished image of the two slits appears. Then once again measure this distance d2. So enlarged and diminished image appears. So when this object distance and image distance changes. See here, one is u, v, and this is v and this is u. If d is actual distance between the images, then your d1 upon d in the first case will give u by v. What is u? Object distance and image distance. In the second position, so d2 upon d is v by u. It changes. d1 and d2 are the virtual distance, d is an actual distance. Magnification is. Then if you multiply these two, you are going to get this is d1 d2 upon d square is equal to 1. U cancels, v cancels. Then your d is square root of d1 and d2. So d1 is the distance between two enlarged image, d2 is the distance between two diminished image. So by knowing d1 and d2, you can find out what is d, and by substituting all these in equation 1, that means beta d and capital D, you are going to determine so wavelength of the monochromatic source. Next you have to study determination of thickness of thin film using biprism. They will ask this as a 5 marks question. So here S1 and S2 are two coherent sources obtained using Fresnel biprism, and at certain distance screen is placed. Now wave travel from S1 reaches the point O. Wave travels from S2 also reaches the point O. Here from this it is clear that this S1O is equal to S2O. This length is same. Means path difference delta S1O is equal to delta S2O. Means path traveled by the two waves is same. In other words, the path difference is zero. Or in other words, you can say that the two waves are in phase. If path difference between them is zero, tell me whether this point O is bright or dark. So if path difference is zero, constructive interference takes place. Definitely this point O is a bright point. And consider one thin plate of glass, or it is mica, say it is of thickness T. If this thin plate is introduced in one of the path interfering beam of the two waves, or in one of the paths, here it has been introduced, it is thickness T, then suddenly this O shifts to the point P. What I am telling, O itself will shift. Central bright band will come to the point P. It has moved through the distance x. Then if you remove this, then again this point comes to the P comes to the O. So by introducing a thin film of glass or mica, the fringe system itself will move. Then now the wave which is traveling from S1 travels from here to here in the air medium, again here to here in the air medium, and here to here it is in the glass medium. That means wave enters from air medium to glass, comes out from glass to air. Then path traveled by the wave from S1 is in the air medium, is S1P minus T. S1P minus T will give these two lengths, S1P minus T. And the wave travels through this thin sheet and through the glass medium it travels the distance T. This is air medium and this is through glass plate. Then I can write what is optical path difference. Optical path traveled by this wave is equal to, it is delta S1 is equal to, in air medium this is S1P minus T plus in glass medium mu into T, where here mu is the refractive index of this glass plate. So call this equation as 1. And from S2 to P, this optical path difference delta S2 is equal to what? S2P. Because it is in the air medium, no glass medium is there, optical path difference is delta S2 is equal to S2P. Then you know that at this point it is a bright band. It has shifted from O to P. What is that path difference? Path difference should be same or 0. So for this your delta S2P is equal to delta S1P. What is this delta S2P? Delta S2P is S2P is equal to this delta S1P is this S1P minus T plus mu T. Then this is S2P minus S1P is equal to mu T minus T, or this is S2P minus S1P. You take that T outside, inside the bracket mu minus 1. What is this S2P minus S1P? S2P minus S1P is the path difference traveled by the two waves. That is, path difference is equal to T into mu minus 1. Then in bioprism experiment, what was the expression for path difference? For path difference, you have obtained this xd upon d is equal to T into mu minus 1. This has came from previous class. So from this your T is equal to x d upon d into mu minus 1. So this is the formula from which you can determine the thickness of the glass plate. What is x? X is the shift in the fringe position. D. What is that D? D is, you know from previous experiment, it is the distance between two coherent sources. And what is this capital D? Capital D is the distance between the coherent source and the screen. So if you substitute all these values, you can determine the thickness of a glass plate.